Thank you, everyone. I wasn't expecting this music, but thanks for sticking up for the last talk of the session. So let's get into it. So I'm here to talk to you about QCLearn, and QCLearn is a quantum machine learning library. And what is quantum machine learning? Let's start with a simple question. So quantum machine learning is a combination of two things. The first thing is quantum mechanics. So we have quantum mechanics, which is probably the biggest scientific revolution of last century. It kind of changed the way we look and we understand at the world. And on the other hand, we have machine learning, right, which is probably the biggest revolution of this century so far, with many important applications. Maybe ChatGPT is not the best one of them, but we have all heard about many different applications of machine learning. And then when you try to put these two things together, you come up with this quantum machine learning, right? So the question is, what can we do when we combine quantum information and machine learning? So a couple of remarks just to start with. The first is that I want to make sure, and I think I'm preaching to the choir here, that quantum is a fundamentally different way of doing computation, right? It's not just a faster processor. It's a very different way of doing computation, which can be much better for certain tasks, okay? And for that, on one hand, we need quantum computers, some kind of quantum machines that can manipulate qubits, right? But we do need a second very important element to this story, which is quantum algorithms. We need to come up with new ways of using these quantum machines in order to be able to start talking about novel applications in areas that could, go through many different domains, things like life sciences, finance, and we do have examples of such applications based on quantum machine learning algorithms. So this is exactly what we do in QC Ware. We design novel quantum machine learning algorithms. This is a list of some of the works we have been doing recently on the machine learning side. I'm not going to go through any of these, but the other thing that we do is that we work with real-world use cases, right? We have a large roster of customers that they come to us with specific, or we discuss and we come up with specific use cases where we want to understand really what is the power of quantum algorithms and quantum machine learning for these particular use cases, okay? We also try to run these quantum machine learning algorithms in the NISQ machines that we have today. We had to develop specific tools in order to be able to take advantage of the NISQ machines that we have today, okay? We cannot offer a quantum advantage today on the NISQ machines that we have today. If someone says so, then start talking to other people. So we cannot offer that, but it is very important to start benchmarking this quantum hardware and figuring out how far are we from a real quantum advantage, in particular when it comes to quantum machine learning. But the other thing that we are doing is that we are not waiting for the quantum computers to come. We also turn these quantum ideas that come from all these mathematic tools that we have developed over decades, if not centuries, to study quantum information. We turn these quantum ideas into powerful machine learning models and methods that we can run today on GPUs, okay? So what are these methods? Let's see a little bit what happens under the hood. One of the methods that we have used in many of the use cases that we will see is what we call determinant unsampling. So if you don't know what this is something that was invented in the 70s in order to study fermionic system. So it's actually a quantum idea that we can take and start understanding how useful it is in machine learning. And it's actually very useful because it can diversify the way that we deal and we sample from data, and this can improve a lot accuracy and prediction accuracy through these ensemble methods, for example, random forest. I think this is running by itself, so I would just ask someone to stop the running by itself, the slide. But if not, I have to go much faster than I used to. So the second method here is this orthogonal and graph neural networks. This is another example where we can use quantum properties in order to enhance what we can do with deep learning and classical neural networks. Here we're using this notion of orthogonality, which is a very quantum property, unitarity or orthogonality. It can improve the interpretability of the models. It can also avoid things like trainability issues when we have very deep architectures, neural network architectures. We can also think of subspace learning. Subspace learning is something which is quite difficult to use classically. We can show that quantum computers can be very good at using this type of methods, right? And the reason for that is that there are very, very somehow close relations between what a quantum computer can do and how to deal with data as points in these manifolds and start talking about subspaces. I'm going to skip the other 3 techniques you saw here. Compound kernels, topological data analysis is something that you might have heard. Manifold optimization. Go to the next slide. Otherwise, it will go by itself to the next slide. So I'm going to start talking about some of the applications that we have seen so far, and I start in finance. Okay, so here is one example. We worked with Itaú. Itaú is the biggest bank in Latin America, and they came to us and they said, here is a very concrete use case. We have our customers, we have their financial data for what kind of transactions they have done in the last year. We need to predict whether they will stay or leave the bank in the next 3 months. Okay, we have a model. It's using a random forest method. Can quantum or quantum-inspired methods do better for us? Okay, so this is exactly what we worked on. We used these determinant point processes, as I said, that were first done for fermions, but now can be used in machine learning, and we improved by 7% the in-house, in-production model that the bank uses today. Okay. Here is a second example. Here we had to come up with ideas on developing and designing quantum neural networks, right? And we did this in order to be able to assess the credit risk of small and medium enterprises. So a small or medium enterprises comes to the bank, they ask for some credit. The bank needs to predict if they would be okay, if they should give the credit, or if they will default, right? How do we predict this behavior from whatever financial data we have about these companies? Here again, we developed some quantum methods and some quantum-inspired neural network methods, and we managed to get higher precision with architectures that have fewer parameters when we run them on the GPUs. Okay. Third example in finance, this is the work that we very recently did with JP Morgan. Here we looked at deep hedging. Deep hedging is the idea of using deep learning techniques for the problem of hedging derivatives, right? Actually, JP Morgan were the ones who invented this in the classical settings. So we tried to understand whether adding quantum to these machine learning methods, and in particular reinforcement learning, if we could add something to what they could do, right? And here the idea of why quantum can be very interesting in this type of use cases is because the main problem about this case is that you have to predict today something that will happen, let's say, in the next month. You have to predict whether how the prices are moving and what kind of strategy you should do today, even without knowing what this future is going to be. So in fact, the problem is that there is an exponential number of possible futures that, the stocks can go up and down according to the stochastic processes. So the main problem in the classical case is that you have this kind of exponential distributions that you're trying to learn something about. But quantum is actually done for dealing with exponential distributions because a quantum state can be associated with an exponential distribution. So using these ideas of how we manipulate distributions in the quantum case, we could come up with some new ways of dealing with quantum reinforcement learning that can actually we could actually show that they could improve on the baseline classical technique of thinking of how to do it through the Black-Scholes models. There are many more type of use cases that we can think of in the finance case. I'm not going to go through all of them. I think finance is a very interesting case for quantum computing and quantum machine learning in particular because we have to deal with this kind of stochastic processes, the ways that we model these markets. And if we look a little bit more at the mathematics of this, of how do we model these stochastic processes, there is a very, very important and strong connection with when we deal with quantum systems. They kind of have the same rules that are applied, and using mathematics and tools from quantum mechanics and quantum field theory can say something extremely interesting about finance. Let's move on to life sciences. Now, I will try to go a little faster. There are, again, many areas in life sciences where quantum can do well, right? One of them is diagnosis, right? In the sense that we have medical images, we want to look at the medical image and be able to help a healthcare professional to decide whether there's something wrong with what we see or not. one particular case where I think is extremely important is when these images come from things like MRIs. And why is that? Because there you're actually having a quantum sensor which is taking data, right? And we are recomposing this quantum data into some images that the doctors can actually see and figure out what's happening in a patient. So thinking about how a quantum computer and how quantum machine learning techniques can be combined with these quantum sensors that actually produce these MRI images is an extremely interesting use case for us. We worked with AstraZeneca, and this was on the clinical trial side. The main problem there is that people sign up for clinical trials, they drop off after a while. You have all this data that you want to use in order to predict whether this medicine will be successful or not, but there is a lot of data which is missing. So how do we fill in this data? Well, again, we can start using these determinant point processes, and what we showed together with AstraZeneca is that not only can we improve on the classical methods like mice or Miss Forest, but we can also do it in a way which is robust, meaning that every time you fill in the data, you do it in the same way, which is something very important if you want to also go through regulations and be able to use these things actually in practice. Drug discovery, this is also an extremely important thing where you can imagine trying to combine, on one hand, quantum machine learning, on the other hand, quantum chemistry and quantum chemistry simulations, and putting these things together. What we hope to achieve is be able to predict properties, molecular properties, things like toxicity or bounding affinity, in a way which is better. And the tools here, the mathematical tools that we use, one of them has to do with topological data analysis, which is one of the areas where quantum algorithms have been very prolific. Okay, I think I talked a lot about quantum applications. You can see that we work a lot with many different companies. So how do we do all of this? We are doing it through our brand new quantum software library, which we call QClearn. So what is QClearn? QClearn is a software library. It's both for data scientists and for quantum developers. It's available on AWS, right? And it extends widely used machine learning libraries that any data scientist knows how to use. Things like scikit-learn, PyTorch, or JAX for neural networks. And it runs both on classical hardware, on CPUs, GPUs, TPUs, and on QPUs, on quantum processing units, through, for example, Bracket or IonQ. What does it do? Well, as I said, it turns these quantum ideas, and I gave you some hints on the mathematics behind these quantum ideas, it turns them into powerful machine learning tools that can do two things. They can lead to better models today, and this is when we take these ideas and we turn them into GPU-based methods that give you models today. And second, they are also QPU compatible today, meaning that you can take the algorithm and run it directly on a quantum computer. Of course, you have to scale down a bit the problem because the quantum computer is smaller, but in some sense, you don't have to worry about whether you're running it on a classical hardware or on a quantum hardware. The algorithm will choose the best hardware available at this moment. At this moment, it's probably a GPU. In the future, it can be a QPU or going back and forth between the two. It can be used, as I said, for quantum proofs of concept, right? This is what we have been doing with our clients. It can be used for data science explorations, and it can also be used for machine learning workflows in production. And actually, we have some of our POCs that we did with clients before. They are in the process of putting these methods in production because, as I said, we do have this quantum-inspired version of the methods that can run on GPU today and improve performance. Okay, how does it look like? So it looks somehow like this. If you're a data scientist, then if you want to use a random forest classifier, then what you do is that you go to scikit-learn, you import your classifier, and you train it on your data. If you want to use our method, then you do exactly the same thing. You're just importing our own random forest classifier from QClearn. You run the model, and many times you can get better results that you would get by running the scikit-learn or the open source methods. And at the same time, our QClearn, because we're talking now about the GPU-based version, on this DPP random forest classifier, it's extremely fast compared to the open source DPP methods which were out there that were not able to run in GPUs or in multi-GPUs as we are. Here is another example. Actually, just to continue this example, if you want to actually now not use your GPUs, but use your quantum computer, you just need to set your backend to be a quantum computer. And here, we're just using IonQ through bracket. And once you put this into your code, then your algorithm, your DPP random forest, will be able to use your quantum hardware to run part of this computation. Here is another example. Here we're talking about neural networks. I think everyone who has used neural networks knows PyTorch. So here is how you would define your own neural network in PyTorch with classical linear layers. If you want to add some quantum layers into these architectures, then you can use our extension of PyTorch, the QCLearn extension of PyTorch. You can define different types of quantum layers. Here we're using what we call these ortholinear layers. You can add them together with any layer that you have from Torch. You can keep everything the same, and now you're running a hybrid neural network architecture that has both classical and quantum layers. Everything goes through, the training goes through, and you just have to make these small changes in order to be able to run now quantum neural networks or quantum-inspired neural networks as you were running classical ones. Again, we can get very good results and better accuracy after a lot of hyperparameter optimization. These are not simple things to get better accuracy, right? These are not out-of-the-box algorithms. You need to work on it, as we also work on it, but it actually works. Okay? And again, if you want to send it to your favorite IBM Q machine, you can just set the backend to that, and as long as you are using things that fit into the quantum computer, you have nothing else to change. It goes to the quantum computer, it gets the results, and it continues the computation. Okay, features and roadmap of QCLearn. As I said, we discussed determinant sampling methods, subspace learning. We didn't talk a lot, but these are important methods when you have dynamic type of data, things like time series or things like videos, where there is this extra dynamic aspect of the data, and this is where subspaces are extremely important. Neural layers, as we said, many different types of architectures, including transformers. This is the T from the chat GPT. We use transformers for vision, actually, with ROS for medical images, but these kind of techniques can be used across disciplines and across domains. We will be putting reinforcement learning there. This is based also on, as I said, what we have done about in the finance side. And more features. We have multi-GPU capabilities, a number of different backends coming from Bracket, IBM. The software is ready. You can even define your own quantum backend, and we will be adding more backends together with new quantum ideas and quantum-inspired ideas, including tensor networks, matrix reconstruction, and Grassmannian optimization. So let me summarize. So we talked about QCLearn. This is our brand new quantum machine learning library that we are very excited about. And what does it offer? It offers ease of use and compatibility for data scientists. I think it was hopefully clear to you all that a data scientist can start using these quantum-inspired and quantum methods. It provides fast GPU methods for better models today. We have concrete examples of use cases where this actually happened together with our customers, and we can provide these better models today. And we provide optimized quantum algorithms for benchmarking also today. You can run benchmarking on your quantum hardware. We cannot get better results today on quantum hardware that we're getting on our GPUs, right? But the algorithm is there, it's optimized, it runs on your quantum hardware, and the moment the quantum hardware gets better, then your algorithm automatically will also get better. There is one last thing that you can do today, many things you can do today, and this is actually ask for a free trial. Come to the booth. We are very happy to give you a live demo. Or go to qcware.com/qclearn. There is a registration form. Tell us that you want to try our QCLearn library and why, and we will be rolling out private free trials in the next couple of months. So thank you very much.
Thank you, Iordanis. We have time for one or two questions. Two questions already.
No, it's very interesting talk, Iordanis. You mentioned about this determinal point processes, right? And you have shown how you boost that. My question is about how does it compare with Gaussian processes, which we use a lot in the classical domain?
They are doing kind of a different thing. So the idea of these determinantal point processes is you have a lot of data, you need to pick a subset of data to use it in order to train your model, let's say. So the way usually we pick the data is that we randomly pick some data. The problem with that is that there is a lot of bias in that because you are picking much more of the things which are popular than of the ones which are a bit rare, let's say. So what this determinant point processes does is that it picks subsets of points that maximize the diversity of the data. Okay? So it picks points whose volume somehow is as big as possible. Right? This is what fermions do because they repel each other and they go to positions which are kind of further apart, right? And this is what we need to do in order to make the data more diverse and hence improve the accuracy and make our models much more robust actually to these outliers.
Thank you.
Thank you for your talk. My question is about in industry we are interested especially to equivariant neural network, what we call geometric deep learning, or because for classical convolution we have a very good GPU implementation, but for group convolution we have not. Are you do you plan to work on this topic also? Or?
We already are. We already are. It's an extremely interesting case. I didn't put it there because we are still working on the theory behind, and we only put things on the product when we have a solid theoretical basis for it. But graph neural networks and geometric machine learning is something extremely interesting, both because it's very good for specific types of data, but also because there is a lot of connections with quantum, and when you start talking about symmetries and supersymmetries and how you deal with these equivariants or symmetries of your data. This is also related with topological features and topological data analysis, so we are putting all of this, we are doing the research that we need to do, and we will be putting it in the product soon. And one of the areas where it will be very interesting is for drug discovery, where you have these molecular properties and these molecules in space, which are kind of graphs, basically.
You have so you make reference to scikit-learn, but you have another library that's been developed, which is called Geomstat, also with PhD student and postdoc from INRIA. So
yeah, I'm sure there are hundreds of libraries of machine learning there. And I'm happy to look at it when it comes to geometric machine learning, but you're right, the best geometric machine learning, let's say, library is not in scikit-learn, right, of course.
One last question, maybe? Anyone? All right, otherwise... Oh yeah, go ahead.
They will think I put you there.
Yes. Iordanis, you mentioned about this manifold optimization. I mean, this has an immense potential in medical imaging, about learning shapes and all.
Yep.
So did you compare with the classical methods of learning shapes with respect to the quantum methods?
Yeah. So we are starting to do the first experiments on that, right? This is why I also said it's something that will happen in the manifolds in Grassmannian. We did a very simple benchmarking where we looked at cells which are illuminated from different places, right? And the question is, how do you now differentiate different cells? Because the images are very different because you have different lighting, for example. So you need to combine all these images together of particular molecules, see them as points in this Grassmannian manifold, and then start thinking about how do you deal with points which are close together or not in a space which is not a flat space now, but actually a curved manifold. And this is where this Grassmannian theory goes, and DPPs are also very connected to that. This is one of the to me, most surprising and amazing things that quantum algorithms are good at. It's exactly this type of things beyond linear algebra.